All right. Okay, my screen sharing is on. Wait a minute or two for more people to log in. Okay, it's 10 o'clock. So first, I want to say that if you want to learn more relativity, a really good book for doing so is Special Relativity in Classical Field Theory by Susskind. I've mentioned some of the Susskind books before. They're essentially a much gentler version of Landau and Lifshitz. The same concept, what is the minimum that you need to start really learning something, except that this is, well, okay, I can make a whole bunch of jokes about American versus Russian education, but this really is a much more realistic picture of the minimum. Landau's idea of the minimum is more like the minimum needed to win a Nobel Prize, which should tell you everything you need to know about the differences between American and Russian education, and why I'm still upset that the Russians didn't take control of the Department of Education. I want the Russians hacking some school board elections. But anyway, Susskind's books are really good. I like his book on the principle on classical mechanics, which covers the principle of least action. His book on special relativity and classical field theory is also pretty good. It shows the ties between electricity and magnetism and special relativity. And of course, this alone is not enough either. To really learn relativity, I would say that you need to study at least this, plus the book we're using right now, plus the Feynman lectures, and then start on general relativity. And I hope that Susskind releases a general relativity book soon. With that said, okay, so today we're going to talk about how velocities change when we go from one reference frame to another. A first fact we need to establish is that no matter how the velocities change, nothing's going to go faster than light. Let's say we've got a train going to the right at beta equals 0.6, that's relative to the ground. And then a person inside the train car for some minuscule fraction of a second runs at a speed of 0.6 relative to the train. Well, according to Galileo, Vx would just be beta plus Vx prime, or 1.2. But this is impossible. First of all, the space-time interval between two events would be imaginary, because we've got delta t squared minus delta x squared. And if delta x is v delta t and v is bigger than 1, then delta x is bigger than delta t, so delta s squared is imaginary. Now, there are, of course, events on the diagram that are separated in such a way that delta S squared is negative and delta S is imaginary. But we don't have people running between those pairs of events, nor do we have spaceships or subatomic particles traveling between them. Likewise, the square root of 1 minus v squared would be imaginary. But then maybe one of the most interesting things is causality. If it were just math, but a lot of advanced realms of theoretical physics use a lot of pretty esoteric math. There's always the possibility that somebody would work out a mathematical framework in which we could have motion faster than the speed of light. Maybe they'd work out some mathematical framework where instead of using complex numbers, we're using some higher dimensional mathematical object where all of this can be fit together. You can always ask that question. But it turns out we would also lose causality. So let's look at events A and B on this diagram. And on this diagram, delta x is clearly larger than delta t. And then let's jump to a new reference frame. So we've got new x prime and t prime axes. Now remember, the x prime axis is just a set of events where t prime equals 0, just like the x axis here is a set of events where t equals 0. And the t prime axis is a set of events where x prime equals 0, just like the t axis is a set of events where x equals 0. And so if you look at this, all right, if we take this event B and we travel parallel to the x prime axis in this plane to see where it intersects the t prime axis, we get that event B in some reference frame precedes event A. So in one reference frame, we've got a person going from A to B. Their departure from A causes their arrival at B. But in another frame, their arrival at B happens before their departure from A. And that would be even more messed up than anything else we've learned in relativity. Any questions so far? Well, one question you could ask is, hey, isn't it okay to disagree on the order of two events? Yeah, but when that happens, neither event caused the other. I mean, our classic example, a light flash in the middle of a train car. As far as the person on the train car is concerned, the light gets from the middle to the left and the right at the same time. So these two events are simultaneous. But event A didn't cause event B. I mean, yes, they have a common cause. They were both caused by something going off here. But having a cause in common is different from one thing causing one another. My brother and I have the same two parents. We have a cause in common. I am not my brother's father, even though sometimes my mother would make me take responsibility for him. So likewise, these two events are caused by the same thing, even though they do not cause each other. So it's perfectly fine that in another reference frame, somebody thinks that event A happened before event B, because event A didn't cause event B, and there's no way that anybody could move fast enough to get from event A to event B. So these two events aren't causally connected. That's the formal terminology, because delta t is less than delta x. And this fact is going to be true in different reference frames. Different people might disagree on what delta t is. They might disagree on what delta x is, but they will all agree that delta t squared minus delta x squared is negative. And so our terminology is that they aren't causally connected, or they have space-like separation. And space-like separation is just a fancy way of saying that these two events could have been at the same time but at different positions. Conversely, if delta s squared is greater than 0, well, then delta t is greater than delta x. Now they have time-like separation. We can find a reference frame where delta x is 0 and delta t is non-zero. And then finally, we can have light-like separation. And in light-like separation, delta t is equal to delta x, So delta S is exactly 0. And that means that as far as light is concerned, nothing has ever happened. As far as light is concerned, the universe is just getting started. Light from the Big Bang has experienced 0 time delay since the origin of the universe. Any questions?
When delta S squared is less than 0, is there another pair of 2 words that we can use to describe that?
Delta S squared is less than 0. Usually space-like separation
Okay.
or not causally connected. So if we look on this diagram, here's an event A at the origin. Anything up here could have been caused by A. Doesn't necessarily mean it was caused by A. I mean, imagine 2 events. Event 1, I'm sitting here giving my lecture right now. Event 2, an hour from now, somebody buys a pizza. There's no connection between these. An hour from now, somebody less than a light hour away, so anywhere on Earth, buys a pizza. There's no actual cause and effect between those two unless you get inspired right now to eat pizza because I said that. So it doesn't necessarily mean that in physics, 2 events with time-like separation are causally connected, okay? It just means that they could be. And all of these events down here, these could have caused A. Doesn't mean they did cause A. I mean, there was probably a magnitude 2 earthquake somewhere on Earth, just because there's always magnitude 2 earthquakes. None of those magnitude 2 earthquakes last night caused me to make the example of pizza. These events in these regions of the space-time diagram could not possibly be caused by event A because they have space-like separation. Any questions? Then I've got some questions for you. And for some of these, we should be able to vote. Not for the first group, but for all of these events, all the possible pairs of events on this diagram, try to figure out what the space-time interval between them is. Is it time-like, light-like, or space-like? So think about that for a minute, and then we'll go through them. Okay, so let's just go through these. A, B, their separation is time-like, basically because delta t is large and delta x is small. For AC, it's space-like because delta t is 1 on this diagram and delta x is large. For AD, it's also space-like. Delta t is 2 and delta x is 1, 2, 3, 4. For AE, it's time-like because delta t is 2 and delta x is either 0 or very close to it, depending on how you look at this diagram. For BC, it's light-like because delta t is 2 and delta x is 2. So light could travel from event C to event B. For BD, it's space-like because delta t is 1 and delta x looks like 3. And for BE, it is light-like because delta t and delta x are both 1. For CD, it's light-like. Again, delta t and delta x are 1. For CE, it's space-like because delta t is 1 and delta x is 1, 2, 3. And finally, for DE, it's again space-like because now delta t is 0. So you can think of this as just asking what's bigger, delta t or delta x. If delta t is bigger, the separation is time-like. That's what dominates. If delta x is bigger, the separation is space-like. That's what dominates. And if they're equal, well, then the only thing they can get between those two events is light. And so we won't go through the voting again, but you should just recognize that, again, anything that's separated by either a time-like or a light-like interval could be causally connected. Anything that's separated by a space-like interval, like say here, could not be causally connected. Any questions? Okay. Now, for this one, you should be able to vote if I do it right. Event A is at the origin, the home frame, and event B occurs at t equals 1 nanosecond and x equals 10 nanoseconds. So what would be the minimum x velocity, beta, that another frame would have to swap the order of those two events? And so you should be able to, if it's blocking your view, you should be able to move that polling window around and take a look at the options. And then just think about what T prime would have to be for this event. T prime would be gamma times T minus beta x. And so what value would beta have to have so that T prime is negative? So far we have a whopping 2 votes. Don't be scared, these votes are anonymous. All right, we've got 4 out of 8 people voting. Again, these votes are anonymous. 6 out of 8 voting. I'll take another minute. Seven out of 8. Anyone else? All right, I'm going to end the polling and share the results. And the correct answer is indeed E. So, hey, democracy works even if Russians aren't hacking the school board. What you can see is that T prime is going to be, well, there's going to be a gamma multiplying both terms. So if we're just trying to set equal to 0, that cancels out. We're going to have the T prime is equal to gamma times T minus beta x, or T was 1 nanosecond. So 1 minus beta times 10. So we need beta times 10 to equal 1, or beta equals 0.1. Any questions? Okay. 2 blinking lights are 300 meters apart on a railroad track. And the west light blinks 5 microseconds before the east light. So if you wanted, you can think of event E as happening at t equals 5 microseconds. and event W is happening at t equals 0. Now let's imagine that somebody in another reference frame is on a train and they're going really, really fast. Is it possible for the people on the train to see these two events happen in different order? And what I would encourage you to do is to think about, not just think about the fact that in some of these questions, we've always had scenarios where two things on train tracks can reverse order. Think about the separation between the events before voting. So far, 4 out of 8 have voted. Six out of 8 have voted. 7 out of 8. Last time we got 7 out of 8. Student number 8, whoever you are, just give it a try. Okay, 8 out of 8 have voted. I will share the results. And again, majority is correct. Democracy seems to work. The way to see it is that 3,000 meters is 10 microseconds, which is their spatial separation of these two events. That's larger than the temporal separation. So these are space-like separated. And if two events are space-like separated, then they can indeed swap order. We're going to skip question 5. We're going to go to question 6. So in question 6, we've got an explosion at x equals 0. Light is detected 100 nanosec at x equals minus 100 nanoseconds, and also at x equals plus 50 nanoseconds, event C. Are these two events causally connected? I'm launching the poll. One person has voted. So far, 6 out of 9 have voted. And 8. 8 out of 8 have voted. Student number 9 has fled. Okay, it is unanimous, and you guys are correct. These are not causally connected. Probably for the reason that, again, my brother and I aren't causally connected. I'm not his father or vice versa, even though we come from the same parents. Both of these events come from the same light source, so it's actually not a terrible analogy. But they didn't cause each other, and they're spatially separated by 150 nanoseconds. One of them is 100 to the left, the other is 50 to the right, so that's 150 for delta x. Delta t between them, well, one of them is going to take 100 nanoseconds to get from the origin to that detector, and the other is going to take 50. So delta t is 50 nanoseconds, the difference between those two. Delta x is 150, so something would have to go at 3 times the speed of light to get between these two events. Any questions? All right. Then, let's see, I think in the interest of time, I'm not going to poll on these, but let's just go through the sequence of events. A laser beam is emitted on Earth. It bounces off a mirror placed on the moon by Apollo astronauts, event B, and then returns to a detector on Earth, event C. The detector is 12 nanoseconds from the laser, which is just a way of saying that the detector is not that far from the laser. So the first question is, the space-time interval between events A and B is time-like, light-like, or space-like? Well, it's got to be light-like, because light was present at event A, and it was the departure from Earth, and it was present at event B, hitting the detector on, hitting the mirror on the moon. So that interval is definitely light-like. Now, the space-time interval between events A and C. Let's see here. The time between those events will be however much time it takes for the light to get from Earth to moon and back. That's pretty long. The distance between those events is 12 nanoseconds, which is, a room. All right, it's the size of a room. So that is going to be a time-like interval. Then events A and C are definitely causally connected. Well, if the separation is time-like, they could be causally connected. You cannot say that two events are definitely causally connected simply because their separation is time-like. You can only say that they are plausibly, that they could be causally connected. Here, I think you can make a pretty good argument that they are causally connected. Any questions on this? Then I want to tell you a story about this, because it's actually a story that involves some people I have met through the Optical Society. So the Apollo astronauts really did place a mirror on the moon. It was one of the first things that they did, because they wanted to bounce laser light off of the moon to study the motion of the moon with very high precision. So they put that mirror there, and then that mirror was made by a company that was later folded into a company known as Precision Optical. Precision Optical is in Orange County, and some of the officers of the Optical Society of Southern California currently work there. They weren't on that project. They're a little bit younger than that. But that is a company that we have ties to. And there was a guy named Hal Walker Jr., who was a scientist on that. He was an engineer, an expert on lasers. There weren't a whole lot of those in the 1960s because lasers were fairly new. And so what they did is they fired a pulsed laser through a telescope. They went to Hawaii to use a telescope. They fired a pulsed laser through a telescope, hits the moon, bounces off of the mirror on the moon, comes back to the telescope, and is detected by their electronics. Took a lot of time to get that to work. This is not an easy experiment under the best of circumstances, and using a very early pulsed laser in 1969 was even less easy. And I actually met Hal Walker almost 6 years ago at an Optical Society of Southern California event, where he talked about that famous day in 1969 or I think it was 1969. I'm trying to remember whether it was in 69 or early 70, because it took some time to get this to work once the mirror was placed. And this is actually pretty important for the theory of relativity, because, the orbit of the moon around the Earth is to very good accuracy described by Newton's laws of mechanics. But there are subtleties in the motion of the moon that require very high precision, and those subtleties could be used as probes of relativity. You could use relativity to check those subtleties. And people have been doing this for decades, improving the precision of these measurements. And to this day, the theory of relativity stands up to all of these tests involving laser light bounced off of a mirror on the surface of the moon. And now that I think about it, as soon as class is over, I'm going to find an article that I read like 6 years ago, surveying the state of measurements as of like, well, I think the article was published sometime around 2012. I'm going to find that article on the lunar laser ranging experiments, as they're called, and post the latest on that when we're done with class. Any questions? Okay, true or false? If the space-time interval between two events is time-like, then the order of the events is the same in every reference frame. Every inertial reference frame. Two more people need to vote. Student number 9, you want to vote? Give you a few more seconds. All right, a majority of you said true. Yeah, if two events are separated by a time-like interval, then one of them could cause the other. And if one of them could cause the other, then we'd better have agreement on the order of the events. Otherwise, you wind up with the situation in the movie Back to the Future. That's a movie from the 80s. Those of us in Generation X remember it, where Marty McFly's parents create him, so they are the cause of Marty McFly existing. But Marty McFly goes back in time and causes his parents to meet each other, so that Marty McFly is the cause of his parents, which really screws up the order of events. Any questions? All right, then let's continue with velocities. Okay, so now that we've established the necessity of the speed of light, of all speeds being less than or equal to 1 in all frames, how do we go from one frame to another? So let's say that I'm in the other frame. I'm on the train. And I measure Vx prime as the velocity of some object on this train. But the train has windows, and so the person on the ground is watching that object move, and the person on the ground can also measure its velocity. Well, the person on the ground says that the velocity is the ratio of dx to dt. X and t are given by the Lorentz transformations. So dx and dt are given by the Lorentz transformations here. And we take the ratio of those two. All right, well, we got a bunch of dx's and dt's on top and on bottom. So then what we do is we divide, dx primes and dt primes. We divide top and bottom by dt prime. So we get dx prime over dt prime. That's Vx prime. Beta, you get dt prime over dt prime, which is 1. And beta dx prime over dt prime. So we get this for Vx. So if we know the velocity is measured by someone on the train, we can find what the velocity is as measured by someone on the ground. Any questions? All right, well, one thing I had you check on today's homework was, given this formula, if Vx prime was 1, then will Vx also be 1 or vice versa? So if we just plug in 1 for Vx prime, we should get that Vx is 1. So all of us have to agree on the speed of light. Also, for small beta Vx prime, the denominator is roughly 1 because this term is roughly 0. And so we just get that Vx is Vx prime plus beta, which is what what Galileo said. If you wanted to do it more rigorously, we would do a Taylor series for this thing here, and then we would get that 1 over 1 plus beta Vx prime is 1 minus beta Vx prime. So then we multiply all of that through, and we get two terms that are quadratic in Vx prime or beta. And those quadratic terms, well, you're squaring a tiny number, that's an even tinier number. Any questions? All right, so let's say that I run to the right at velocity beta as measured by you. And my wife runs even faster, so her velocity relative to me is beta, which means that Vx prime is beta. If Galileo was right, her velocity relative to you would be 2 beta. But in relativity, things are going to be slightly different. So the question is, how fast would we have to be running so that Vx is not 2 beta, but 0.9 times 2 beta, meaning that there's a 10% discrepancy. That would be something pretty easy to measure. So what we can just do is we can say Vx equals Vx prime plus beta over 1 plus beta Vx prime, that expression that we already derived. That's 2 beta over 1 plus beta squared. And we want that to be 0.9 times 2 beta. So 1 over 1 plus beta squared must be 0.9. So 1 equals 0.9 plus 0.9 beta squared. 0.1 equals 0.9 beta squared. Beta squared is 1 over 9, or beta is 1/3. So you would have to be going at 1/3 the speed of light in order to see a discrepancy. Now, the practical significance of this is not about people running at inhuman speeds. It's about the microscopic world. Electrons going around atoms are usually going at 1% to 10% the speed of light, give or take. And what I'm saying here is that in order to get 10% discrepancies on relative velocities, you have to be at 1/3 the speed of light. So what you should take away is that even at a few percent the speed of light, Newtonian mechanics could be, well, Newtonian mechanics doesn't apply to electrons around atoms. Non-relativistic physics is a very good approximation, even at a few percent the speed of light. So even in the atomic world, you can get away with ignoring relativity on many, not all, but many occasions. Another example, I see two people coming at me with equal speeds and opposite velocities. And so what is the velocity of the person on the right according to the person on the left? So let's say that I'm in the home frame, all right? So I measure this person's velocity, Vx, as minus beta, because beta is just the magnitude. I say that they're coming at me with Vx equals minus beta. This person is moving at velocity beta, and we're going to say that they're the other frame, so we need to figure out what Vx prime is. Well, Vx prime is going to be Vx minus beta over 1 minus beta Vx, or let's see, minus beta over 1 minus beta times minus beta, or minus 2 beta over 1 plus beta squared. That would be one way to figure this out. The other possibility is to say that I'm in the other frame and I'm moving at beta, at a negative beta relative to this person's frame, right? I see B moving towards me. And so Vx in this person's frame would be Vx prime plus beta over 1 plus beta Vx prime. And now we're going to get 2 beta over 1 plus beta squared. And you may be thinking, well, these two results disagree with each other, except that beta was negative the way I set this up. Either approach will work. Either approach had better work. You would better be able to solve a problem in more than one reference frame and get, if not the same result, then at least equivalent results. Otherwise, the theory of relativity doesn't work. Any questions? Anyone? All right, now let's do 2D and 3D motion. We know that when we switch reference frame, y prime equals y and z prime equals z. So let's say that somebody's velocity v prime is in 2 dimensions, but the relative velocity of the observers is just along the x direction. So Vy has got to be dy dt. And we know that y equals y prime, so dy equals dy prime. T is still given by our Lorentz transformation, so dt is also given by our Lorentz transformation. So Vy is dy dt, or dy prime over dt prime plus beta dx prime, all over square root of 1 minus beta squared. And 1 over something is just that original something. So we get a square root of 1 minus beta squared here. And we get a dy prime over dt prime. And then we divide the bottom by dt prime as well. And so we're left with Vy prime square root of 1 minus beta squared over 1 plus beta Vx prime. It's a more complicated formula. Any questions on the steps that I took to get there? Seeing no questions, let's test it. I asked you on the homework, before talking about the physics of it, to just mathematically try a simple case where V prime is at 45 degrees. Now we're going to do the more general case, where V prime is at some angle theta. So Vx prime would be cosine theta, Vy prime would be sine theta, and we're going to check this. The magnitude of V prime is square root of cosine squared theta plus sine squared theta. That's 1. We want to verify that the speed of this light is also 1. Not the velocity. The velocity of light will change. The velocity of light can most definitely change between frames. It's the speed of light that has to be the same. So Vx, we just plug and chug beta plus cosine theta over 1 plus beta cosine theta. Vy sine theta times that square root factor over 1 plus beta cosine theta. Now we square everything. All right, we square each component and add the squares. Remember, we square and then add, not add and square. There's always somebody who wants to add and square. But we square and then add. So we get this. When we square the first term, we get a beta squared, 2 beta cosine theta, and a cosine squared theta. From the second term, we get a sine squared theta and minus beta squared sine squared theta. Let's see, this cosine squared and sine squared, they add to 1. And this is beta squared times 1 minus sine squared theta. And 1 minus sine squared theta is cosine squared theta, which means that we now have beta squared cosine squared theta plus 2 beta cosine theta plus 1. And the denominator, when we square this, we get 1, we get beta squared cosine squared theta, and we get our cross term in the middle, 2 beta cosine theta. So the top and bottom are equal. And these formulas are consistent with our key assumption. Any questions? Anyone? Anyone? Bueller? Bueller? Okay. Now, here's the final piece of weirdness. Velocity transformations along different directions don't commute, which means that if I apply them in different orders, I get different effects. So let's say that beta is, I'm just sitting here. Somebody is moving at velocity beta to the right relative to me. So they're going to the right. And in their reference frame, they see something going straight up. This would be like if you're in a train car and you just toss something straight up in your hand. As far as you're concerned, tossing something straight up in your hand on a train car, it just goes up and down. But to the person looking at it through a window from the ground, it's going up and to the right. And so we want to figure out what these velocity components are. So it's pretty straightforward. Vx prime was 0. So Vx will just be 0 plus beta over 1 plus beta times 0, or beta, 0.6. Nothing spectacular there. Vy prime, sorry, Vy will be Vy prime times the square root factor, and Vy prime is 0.8. And that square root factor is 1 minus 0.6 squared. 0.6 squared is 0.36. 1 minus 0.36 is 0.64. And the square root of 0.64 is 0.8. So we get 0.8 times 0.8. These are our values for Vx and Vy. Any questions on those? Hearing none. Let's reverse things. Suppose we had a different experiment. Suppose that, again, the home frame is what we define to be standing still. But now I'm going upward. I'm going in the y direction with beta y equal 0.8. And we're calling it beta y. We've never done that before. We've always just said beta is implicitly in the x direction. But now we're switching things around here. And so the relative motion of our frames is in the y direction. So every formula that we had, we have to switch x and y, because now the relative motion of our frames is in the y direction. But the relative motion of our frames in the y direction is still at a speed of 0.8. So beta y is 0.8. Vx prime is 0.6. So now, every formula that we had for Vx, now it's a formula for Vy. And the reason why is that the laws of physics don't care about x and y. The laws of physics only care about, there's the direction of relative motion, and there's the direction perpendicular to relative motion. Call it x, call it y, the laws of physics don't care. The laws of physics are totally Shakespearean. What's in a name? That which we call a rose would by any other name still smell as sweet. Oh, what is a Montague? 'Tis neither hand, nor foot, nor any other part belonging to a man. Sorry, I love Shakespeare, and I really hope that summer Shakespeare festivals aren't canceled. I will be so pissed if they're canceled. Anyway, when we plug all of this in, we get that Vy is 0.8, whereas before we got 0.64. And we get that Vx is 0.36, whereas before we got 0.6. Now, this is very, very different. So the order in which we switch reference frames, the order in which we add velocities, talking about what is relative to who, that matters a lot. Now, I said last time that, not last time, the time before, that these Lorentz transformations were kind of like rotations in a hyperbolic space. And it turns out that just like the fact that these changes of velocity don't commute, meaning that if you take something moving in the y direction relative to a frame in the x direction, that's different from taking something moving in the x direction relative to a frame in the y direction. It all comes down to the fact that you're asking, well, who's measuring the time? Is the person measuring the time going at 0.6 relative to the home frame or 0.8? That's the physical origin of it, but the result is that these things don't commute. Turns out the rotations don't commute either, meaning that the order in which we do rotations is changed, that the order in which we do rotations matters. Let me give you an example. Here I've got a magazine. I'm going to first do a rotation about the horizontal direction, right? The direction that is into the camera. And then I'm going to do a rotation about the vertical direction. And what we've got is we've got this upside down advertisement for MATLAB. All right, so I did horizontal direction, vertical direction, and we got upside down MATLAB. Now I'm going to do vertical direction. Wait, no, that's because I did 180 degrees instead of 90. So let's do horizontal direction, vertical direction, and I get MATLAB add with the spine of the magazine up. All right, so horizontal, vertical. Now, let's do vertical, horizontal. I again get a MATLAB add with the spine of the magazine down. We could have done 45 degrees. We could have done horizontal, vertical, and wait, one last time. Horizontal, vertical. I get the magazine looking into the page with the MATLAB add on this side and the cover on this side. Whereas if I had done vertical, horizontal, I would have gotten it reversed. Anyway, you can play with those rotations at home, doing them in different orders, and you'll get different things. That's related to the mathematical analogy between changes of reference frame and rotations in a hyperbolic space. Any questions? Well, seeing no questions, have a good day. As always, I'm available if you have questions outside of class. And on Wednesday, we will start talking about energy and momentum in relativity. Have a good day.